Yeah, okay. So, hi, my name is Bengisu, and yeah, I'll just skip the introduction then. I completed my master's degree in Bogazici University under the supervision of Arsjan Özgür, and now I'm working at TÜBİTAK as a research and development engineer. And now, today I will present our study named Ontology-based Protein-Protein Interaction Explanation using large language models. And here's our outline. I'll just skip it now. And let me begin with the introduction. So as we all know, the biomedical relations between the entities are represented with the relation keywords. And these relation keywords often infer the relation type. So they can be used to, analyze and understand the interaction between the biological entities. So our goal is to explain the relations by identifying relation keywords in a sentence. To find these relations and explain them, we use Llama 2. Why we have chosen it? Because it's a GPT-like architecture and it's great for generation tasks. And on top of all of these, it's the model parameters are open sourced, so it's really great to do additional fine tuning or further pre-training. So here is a small example of an interaction sentence. The orange ones are the entities, and the blue word represents the relation keyword. In our previous study, we have collected 826 interaction keywords, such as binds, interact, activates, and etc. And to some of them are the variations of the same words. For example, there is binds and bound. They are actually, represent the same interaction, but they have also exist in the ontology we have. So the Interaction Network Ontology is actually a literature mining tool to support the ontology of these interaction keywords, and it represents the various types of these interactions. If you look at to the literature, we can definitely say that with the discover or creation of the transformer architecture by the VDOS2024 et al., the era of large language models has begun. And in our previous study, we have used these transformer architectures in different ways. For example, we used the ChatGPT, and we evaluated the zero-shot performance of ChatGPT and compared the results with the fine-tuned BERT-based models such as BioBERT, SciBERT, PubMedBERT. And we evaluated the performance and compared them on different protein-protein interaction data sets. And our results show that while ChatGPT performed competitively with carefully designed prompts, the BERT-based models that we have fine-tuned were superior. Some other studies also investigated the performance of the LLMs, especially on zero-shot and few-shot setting, and they did different evaluations and showed their performances and which is good on which task and etc. Also, there are other fine-tuning techniques like parameter efficient fine-tuning. It's actually a similar way of fine-tuning, but rather than fully utilizing or updating all of the model layers or just couple of layers of the model, we rather use a small set of additional weights, and then we fine-tune it on the new task we have. And these new updated weights are somehow merged or mixed with the original model parameters. Then we have a updated and fine-tuned model, and this is called the parameter efficient fine-tuning, which is called PEFT in short. There are other large language models, especially developed for biomedical applications like PMC, Llama, or Meditron. We'll just skip this, and if you want to look at the details, you can always take a look at them. So in our study, we have used actually the learning language and logic LLL dataset, but this time we used the I know version of that, which is actually the interaction sentences are tagged with the I know keywords. So the I know has 575 terms, and they fall into 202 interaction branches. And we can see the branch details here. Here's an example of an I know branch. We can see that the interaction keywords are, in a tree shape. And so there is a class hierarchy in the I know, and we use the LLL I know data set to explain the relations of the entities, actually. So just before doing any further analysis with the data set, we pre-process the examples one by one. So for that, we used a similar strategy, which was proposed by Li et al. And here we actually enclose the interacting entities with the protein 1 and protein 2 tags. So this protein tagging strategy is actually helpful to indicate which proteins are interacting with each other while keeping the protein or gene information inside a sentence. So we're not covering the protein name, we're just keeping it and we are enclosing it. So in total, we can say we have 164 number of interaction sentences, and to do any additional fine-tuning or other steps, we split the data set into train, validation, and test. So this is our distribution. So let me just start with our methods. And first, we used in-context learning. And in context learning, we have developed two different strategies, and we compared its result. One is the zero-shot setting, and second one is the few-shot setting. So other than that, we also looked into the parameter-efficient instruction fine-tuning method. So let me go into detail. So in the in-context learning, we can say that it's still a powerful method, even if there is no gradient updates. So we're not actually training the model, but we are just giving the test example, but still the model can learn from what it's seeing at that moment. It's still shown that it's a great method in some tasks. It can be applied. So we wanted to compare its scores with the other methods. So here in the zero-shot setting, as we can see in the image, we have an introduction. So in the introduction, we're just defining our problem, and we're just saying what we want from the model. We say below is an introduction that describes a task. So write a response that appropriately completes the request. And then we are providing our instruction. And in the instruction, we are actually giving our test sentence. So what is the question sentence? So the question is, what is the keyword that represents the interaction between the proteins which are tagged with protein 1 and protein 2 in the given sentence? Next, we are providing the test sentence, which is already tagged with the protein tags in the pre-processing step. We already tagged them. Then we are providing the response key. This response key, we believe it helps the model to respond after that key, so that it shows what we are expecting from the model. And then this is our basic prompt scheme for the zero-shot setting. So in the few-shot setting, it's actually really similar to the zero-shot setting, but since Llama 2 has a large context length, which is 4,096 tokens in a single context, and we said we can maximize the context length so that the model can see as much as examples in one shot. Therefore, we calculated the average token length of the LLS sentences, which was around 80, and then we decided to select 40 number of sentence and their response pairs in one context. So we repeated this experiment for 3 different times, and we averaged these 3 experiment results because in each experiment we have selected different 40 number of context response and sentence pairs. So here is a scheme for this one. As we can see, only difference from the zero shot is actually we have a context here now. And in the context, we have n number of examples and their response pairs, but we have selected it as 4D, and we repeated this experiment for 3 different times with and selecting different number of context examples. And our other method is actually the parameter efficient instruction fine-tuning. So again, we have a similar prompt scheme, but this time, since it's a fine-tuning, the model has to learn from the training examples. So in each example, while we're providing the prompt, we are also giving the response key as well. This is the fine-tuning procedure, and this is called parameter efficient instruction because we use PEFT, as I mentioned earlier, and this is called instruction because we are training with or fine-tuning with the instructions here. Next, we were given a test sample for inferring what is the relation given in the sentence to the model. Yeah. So let's look at our experiments and results. I'll just go over with how we calculate the scores and how the results of in-context learning or parameter-efficient instruction fine-tuning differ. So we'll just take a look at them. So while calculating the scores, we actually used tokenized calculation. And this is how it's done, and let's look at that. We have actual keywords, and we have also the predicted keywords, which comes from the model Llama 2. So before doing any calculation, we just map the keywords to their respective INO IDs to standardize the evaluation of the large language models. And then we map the predicted keywords to their INO IDs as well. And then for each row, let's say here, we calculate the precision recall on F1, and this is called tokenized metric calculation. If we look at our results in context learning for zero-shot setting, we can see that from precision and recall and F1, the Llama 2 7 billion chat model, which is the smallest model of the Llama 2 family, has lowest scores, right? But this was also expected because it has a smaller number of parameters, and the other models, such as 30 billion model, outperform it in a great way, but 7 billion model much better compared to the other two in the zero-shot setting. If we look at the 5-shot setting, as I said, we have we did 3 different experiments, and at the end we averaged the 3 experiments results. So if you look at the average score, we can say that with the 5 shots, with the given context examples, the scores increased in the smallest models higher compared to the larger models, 70 billion models. So it was a bit shocking. First we saw the results because we also expected to see that much of increase in the larger model, but the results are given here. Says that the smaller models can learn from the context better. Probably this was our outcome. And if you look at the parameter efficient instruction fine-tuning results of the Llama 2 models, by the way, I just forgot to mention all these results were, we got them on the test split of our LLM data set, which has 25 sentences. And the instruction fine-tuning results shows that since we cannot evaluate the and fine-tune the 70 billion model due to our GPU requirements at that time, it wasn't available. We couldn't fine-tune the largest model, but rather we only fine-tuned the 7 billion and 30 billion model. And we saw that the scores are really close to each other, and the Llama 2 30 billion chat model actually more precise on its predictions, while the Llama 2 7 billion model were actually more predicted more of the true interaction keywords. And on the F1 score, and they were really close to each other. And we can say that the 30 billion model outperformed the 7 billion chat model on a fine-tuning setting. Also, if we remember the previous results, these two models actually outperformed the zero-shot and fifth-shot setting of the 70 billion chat model as well. So if we just wrap up our results, we can see that the lowest results were from the zero-shot setting, and the largest model, which is 70 billion model, outperformed the 7 billion model by 41.2% on F1 score. With the given context examples in the few-shot setting, the Llama 2 7 billion chat model scores were increased by 43%, more than 43% on F1 score. And for Llama 2 30 billion chat model, the scores were increased more than 90% on F1 score. And for the largest model, 70 billion model, the scores were just increased around 6% on F1 score. And with the parameter efficient fine-tuning, the results were improved, especially if you look at the Llama 30 billion chat model, it outperformed the largest model scores in zero-shot setting with, by 24.13% on F1 score, and in few-shot learning, the model outperformed the 70 billion model on 17.82% on F1 score. So this was just our hyperparameters for the parameter efficient instruction fine-tuning. If you just want to look into detail, you can always take a look at that one, but it's not that important. We obviously did some hyperparameter tuning on these parameters as well. This LoRa hyperparameters indicates the PEFT parameters, and actually says you should give that much of importance on the new pre-trained, new fine-tuned weights compared to the model weights. This hyperparameter just decides on this value. So if we just quickly look at the predictions of our best model, which was Llama 2 30 billion chat model fine-tuned version, we can see some examples from the keywords, which are golden keywords, gold keywords, and the predicted keywords here. We can say it did a pretty good job in this LLM dataset. To conclude, we showed the effectiveness of LLMs to explain PPIs by mapping the predicted interaction keywords to the INO. We explained the relations by generating the interaction terms with the Llama 2 chat models. We proposed an approach which can be used to explain relations between other types of biomedical entities using ontologies and LLMs. We can say that smaller models can be more effective by applying the in-context learning and fine-tuning methods compared to using always and choosing the largest model always. It's not the case, we can say. And instruction fine-tuned quantized Llama 2 30 billion chat model outperformed the largest model in in-context learning setting. And as far as we know, this work was its first of its kind. So thank you for listening. And if you have, we have our code and data set available in these links. And thank you for listening. And if you have any questions, I'll be happy to share and answer.
Thank you very much, Bengisu, for great talk. Do we have any questions for Bengisu, please?